Imagine trying to manage a rapidly growing network with thousands of devices, all using traditional manual configurations. It quickly becomes a complex and error-prone task. This is precisely the challenge that software-defined networking, or SDN, aims to solve by centralizing network control and abstracting the underlying infrastructure. Scalability concerns significantly impact SDN implementation by directly challenging its core promise of centralized control. While centralizing the network's control plane offers immense flexibility and programmability, it can also become a single point of bottleneck for performance and reliability as the network grows larger and more complex. The primary reason for these concerns lies in the architecture of SDN, which separates the control plane from the data plane. The central SDN controller must maintain a consistent view of the entire network state and communicate policies to all data plane devices. As the number of network devices, flows, and policy rules increases, the controller faces immense pressure regarding its processing power, memory capacity, and communication bandwidth with the forwarding elements. This can lead to delays in policy enforcement, reduced network responsiveness, and even controller overload, undermining the very benefits SDN seeks to provide. To mitigate these scalability challenges, network architects often implement hierarchical or distributed SDN control plane architectures. This approach involves deploying multiple controllers that manage different network segments or communicate with each other to share network state information. Another strategy involves offloading complex policy decisions to specialized network applications or leveraging more powerful data plane forwarding hardware that can handle a greater number of flow entries and packet processing tasks. Understanding these scalability dynamics introduces concepts like controller sharding, where the network state is partitioned across multiple controllers, or eventual consistency models, where controllers synchronize their views over time. It also highlights the critical importance of high-performance southbound application programming interfaces, or a PIS, which dictate the speed and efficiency of communication between the controller and the data plane devices. These advanced techniques are essential for pushing SDN deployments into enterprise and service provider scale. Ultimately, successful SDN implementation requires a careful balance between the advantages of centralized control and the practical limitations of scaling that control plane. By thoughtfully designing the controller architecture and optimizing the interaction between the control and data planes, organizations can harness SDN's power for agile network management without compromising performance or reliability, ensuring their network can evolve seamlessly with growing demands.
If you love understanding how the web works, like, subscribe, and stay connected with us.